Talk by Yoram Selzer, moving to a completely different topic, which will be presented hopefully.
I'm going to do, my talk is going to look a little bit different from what you just heard. I'm going to focus on one story. I'm going to go into details in this story, and I will try to make it as clear as possible for the general audience here, so that we'll be able to follow what we've been trying to do in the past few years in this specific project. But I was asked to talk first about what we're doing, and mainly doing, and this is what we do. We are interested mainly in single molecule junctions. We know how to make junctions with one molecule inside. We can prove that there's one molecule conducting in these junctions, and we are interested in the conductance properties of these junctions under several conditions or many conditions. And what we are mainly interested in is how fast do they operate. And theory suggests that they should operate faster by something like maybe 3 to 4 orders of magnitude faster than conventional electronics, which means that we don't have any means to measure these structures or how fast they operate, and we develop methods to follow the transient behavior of such junctions, but I will not talk about this today. But maybe I should say that what I'm interested in basic science. So I'm doing nanoscience, I'm not doing any nanotechnology, but the work that I'm going to describe today has some flavor of nanotechnology. It was done by these 3 former students of mine in the past few years. This is a long project. I like long projects. My students don't. But it's, as you will see, I mean, it's a very interesting project in terms of the science, but also technological. So a few words about thermoelectric devices, and let's focus on this here. Can you hear on the back without the microphone? So let's focus on this. This is the Peltier effect. So if you have a device that you are using in order to do active cooling on one side. So what we are interested is to cool the top of this device. We transfer current through this device so that the charge carriers, because we are using P and N semiconductors, the charge carriers are in both type of semiconductors are flowing in the same directions. So when the charge carriers are getting to the top over there, they are thermally excited, and then they move to the other side and deposit the heat here. So as a result, we have active cooling on the top. So this is a refrigerator, which has several advantages. If you can see here, it's highly reliable. This is a solid-state device, silent, clean power, compact. And you can make, I will show you that we can make nanoscale refrigerators like this. And this is one of the main goals of the field of thermoelectricity. Can we make really small, very efficient thermocoolers? And in order to do this, we need to characterize the efficiency of a thermoelectric device. And this is the figure of merit that you see here, the ZT, which is a factor of several parameters. The first one is the Seebeck coefficient. So if you take a material and you develop a temperature gradient across this material, it develops a voltage gradient, and the ratio between the two is the Seebeck of the material. The other thing that you need to worry about if you want efficient thermoelectric materials is that you should have high electrical conductivity. The higher the conductivity is, it takes heat better, and you need to make sure that the thermal conductivity is as minimum as possible, because then you make sure that if you take heat from one side to the other, it won't go back. So you want the thermal conductivity, which has 2 components, the electronic thermal conductivity and the lattice thermal conductivity. You need this to be as minimum as possible. Now, the best material that you can find in the market has a ZT value of a little bit more than 1. This is what you can get. Okay. Now, if you go to someone that is interested in thermoelectric materials and you tell him, think about the number that he's going to tell you is probably going to be 3. Once we pass 3, once ZT is about 3, it means that we will have thermoelectric devices that are operating as efficiently as household refrigerators. So if you take the efficiency of a household refrigerator and you define its efficiency in terms of ZT, once you have a thermoelectric device with a ZT that is higher than 3, it means that you can cool everything that you have at home with something that is not operating with a compressor or a coolant, etc., etc. So this is the goal. All right. Now, to reach this goal, it's not easy because the parameters that define the efficiency of such a material are interrelated. So what you see here are the different parameters plotted here as a function of the number of carriers inside a material. So as you move from an isolators to a metal, the conductivity increases. Okay, the electronic conductivity increaes. The lattice thermal conductivity is the same, it is by the phonon, so it's roughly the same, and the Seebeck is going down. And since the ZT is what you see here, the maximum ZT is somewhere around here, so most of the materials, everybody is using either semi-metals or semiconductors in order to have really efficient thermoelectric coolers. Now, there's a very famous paper that was published, 17 years ago, that tried to define what should be the best thermoelectric material. And not surprisingly, from the mathematics, you see that if you have spiky density of states, and I will show you in a sec why, if you have spiky density of states, you should see a very efficient thermoelectric material. So the idea is to design materials with spiky density of states. Now, this is difficult, not easy at all. What people actually prefer to do is to work on the other side of the equation, so to manipulate the thermal conductivity, or more importantly, the lattice thermal conductivity. So they either work with alloys, with superlattices, and in both cases, you simply block the way that the phonons are propagating efficiently by changing the structure, or if you have a mismatch in the crystal as the phonons are propagating, they bounce back, so the thermal conductivity is not efficient. And it's obvious that once we get the amorphous limit, once we have a material that is completely amorphous, then thermal conductivity, lattice thermal conductivity is going to be at the minimum, but then it's really difficult to make materials like this that are also very efficient in terms of electrical conductivity, so this is a problem. Now, several years ago, someone said, you know what, let's work with one-dimensional materials in order to have really efficient thermoelectric devices. And the idea was the following. If you look at the density of states of a one-dimensional material, so one-dimensional material means that in this direction and in that direction, the energy levels are quantized. And it's not quantized in only one direction. So if you look at the density of states, it's spiky. This is the green curve that you see here. So here the density of states, the function of energy, is spiky. And I've showed you before, mathematically, if you have spiky density of states, you should have high Seebeck coefficient. So this is one reason why we need to work with one-dimensional conductors. The other thing is that people assume that the bouncing or the diffraction of the electrons on the boundaries of such a device won't interfere much with the electrical conductivity. So it's the effect on the sigma is going to be negligible. But then phonons are going to scatter in a way that will make the thermal conductivity because of scattering on the boundaries, the thermal conductivity is going to be low, and as a result, we expect to see high ZT materials. And here's two papers published a few years ago, back to back, by two quite respectable gentlemen, and they showed with silicon nanowires how they get ZT values in the order of 1 at room temperature, using wires with a diameter of 10 nanometers, 20 nanometers. So their conclusion in both cases was that they were actually affecting mainly the thermal conductivity. All right. Now we thought that if we want to work with one-dimensional one-dimensional materials, why not work with Bismuth? Bismuth has very interesting properties. First of all, the Fermi wavelength of Bismuth is 26 nanometers. It means that once we make nanowires of Bismuth with a diameter that is less than 26 nanometers, we have one-dimensional conductor. And it's easy to make wires like this, very easy. And the second thing is that the mean-free path of carriers inside Bismuth are really, really long. I mean, at 4K, they are extremely long. So it means that we can have, we expect that the electroconductivity to be extremely high if we make short wires. And also the thermal conductivity, lattice thermal conductivity of Bismuth, because Bismuth is a heavy atom, it's gold. And so once we make nanowires, it's going to be even lower. And what you see here is what is happening if you are making nanowires like this made of bismuth. So if you initially start with a semi-metal, so you have the electron and hole bands together at the Fermi level. As you make so this is bulk. And if you are, once you are making wires like this, these two bands are making a gap in between them, so you shift yourself between a semi-metal to a semiconductor, which helps us to get better thermoelectric properties. And a theoretical prediction said that if we have nanowires of bismuth in the order of, let's say, 10 or a little bit less than nanometers, we should expect to see ZT values higher than 3. And this was calculated to 77K because the electronic properties of bismuth are really, really complex, very temperature dependent, and they become much less dependent once we cross below 77K. So this is why they made a prediction at 77K, and all the results I'm going to show you today are at 77K, not at room temperature. All right. So we made a process. I'm not going to describe how to make wires as long as we like based of bismuth, and this is not really important. But we have really very good wires of bismuth that are single crystal, very oriented in several directions, but we can characterize the direction group. And what we do is now we need to measure the different parameters that define the thermoelectric efficiency. And here's the experiment. So here's the wire connected between two gold contacts. Now, in order to make this experiment, you need to have really, really good ohmic contact of both sides. Okay, it's turns out to make good ohmic contacts with bismuth is a very, very complicated process, extremely complicated process because of the oxide which is covering bismuth. It took us 2 years only to solve it, just to give you a feeling of how difficult this is. So once we have the contacts, what we can do is the following. Everything here is on an insulator, so this is on silicon oxide underneath. And then we have a heater. So we pass high current through the heater, and everything here becomes hot, and then you have a temperature gradient across the wire. So if you measure the voltage between these 2 points, you have delta V, which is essential in order to characterize the Seebeck coefficient. The next thing that you need to do is what is delta T between the 2 points, and this is why you have this structure here. We simply make 4 probe measurements and measure small changes in the resistance of this wire here, which is made of gold. And by the change of the resistance, we know what is the temperature that you have on both sides. So we know delta T. So we have delta V, we have delta T, we know the Seebeck. And the Seebeck of the wires that we are making is quite high. It's minus. It should be minus because the electrons are the carriers inside bismuth. But this is really low. We wish to see something which is much better than that. Now, the next thing is that we want everything to be ballistic. Why? I'll show you in a second. So we simply push the 2 contacts on the bismuth nanowire. Instead of being here on both sides, we push them to be really close to one another. And then if we make the 2 contacts at different distances, and we measure the resistance as a function of this length, you see that at a certain for certain distances, it becomes ballistic. The resistance is not changing. So every electron that is coming from one side is going all the way down to the other side without any scattering. So we want to work in this regime. So all the experiments that I'm reporting from now on are with contacts within this length range. So theory suggests the following. Suppose that we have a wire and we shrink it, so that we have the quantized behavior that we have here in the middle. So here's the bent edges of bismuth, and as you make this size smaller and smaller, you get a higher separation, a larger gap between the bands. And if you just model it as a one-band model, you can see that the Seebeck, which is proportional to the derivative of the ln of the conductivity. And if the conductivity here, everything is ballistic, so it's G naught divided by this argument here. I won't go into the mathematics. You can actually get some very simple equation which should describe the Seebeck coefficient as a function of the position of the band edge relative to the Fermi level. So as you make this larger, S is going to be larger, and the distance here is between the dashed line here and the band edge on one of the bands that is more contributing to the conduction. I will skip this. This is telling what I just said more quantitatively, so I'll go straight to the results. So what we do here is we have the ballistic wire, and then we have some kind of a method that we developed that allows us to make this small knot. Right? There's a shrinkage in the size right in the middle, okay, which is, in this case, it's 70 nanometers. And as it becomes smaller and smaller, the conductivity, the conductance is going down, and everything here is reported in units of G naught. So once we are below one G naught, then G naught is one mole propagating from one side to the other, and then we are below. Now, we can do this by changing the size of the constriction, make it smaller and larger, and we change the conductance, and at each point we stop and we measure the Seebeck. So when we are above 1 G naught, the Seebeck is really low, and it's minus. But once we are below 1 G naught, because the Seebeck is really large, and it's positive. The contributing band to the Seebeck once we are below 1 G naught is actually the whole band, and this is what we actually expect. Sorry, oh, this is suddenly working. This is what we are expecting to see, and so we can flip from low Seebeck values to high Seebeck values, and this is really high Seebeck, extremely high.
What distance did you consider for the Seebeck division?
Distance in terms of what? How big is the gap, the energy, in terms of energy? Oh, you can see it here. So if we have here it's several hundreds of millielectron volts. So once we have this, we can actually plot. We can make several junctions like this, and then we plot the Seebeck as a function of G. And if you look at the mathematics, you expect to see S as a function of G going like 1 over G, and this is what the red curve that you see here is the theoretical fitting, which is quite good. So if you plot now the argument that you need to put inside the figure of merit is this multiplication, which is what you see here. So there's a certain range of conductance for which you have a maximum in this multiplication. It's somewhere here, and it fits actually very well to what you expect to see based on the theoretical model. So this is one part. So this is now we have this. Now we need to deal with this. So how do we solve the problem of measuring the thermal conductivity? We do the following. We made a structure which is suspended. So here's the wire above a certain gap inside the structure, and you have contacts on both sides. And what we do is the following. We put an AC current flowing through the wire. Now there's heating taking place due to the flowing of the current. So the temperature gradient is what you see here. It's higher in the middle, it's lower at the edges, and it is fluctuating up and down. Now if you have current, an AC current, going through the wire at a certain frequency, let's say omega, the temperature is going to fluctuate at 2 omega, because the power that you put on the wire is I squared. So if you have a temperature that is fluctuating at 2 omega, it means that the resistance of the wire is going to fluctuate at 2 omega. Now, you have current flowing in at omega and temperature flowing at 2 omega. It means that you have a voltage component, IV, that is oscillating at 3 omega. And this 3 omega signal is free from any other contribution that you can think of that is happening here. So we are measuring 3 omega as a function of the current that is flowing, and you can actually take a theoretical argument or actually calculate what we expect the V3 omega to be as a function of the current. And this is a one-dimensional diffusion problem of heat through the wire. And this is what you see here, the two wires. And this is the thermal conductivity that we measure. This thermal conductivity we extract from these calculations and these experiments is really low. This is in the amorphous fluid. We have a single crystal structure, structure that behaves like an amorphous material. This is very surprising, extremely surprising. But then we had to find out why this is so, and we checked this zillion of times to make sure that we are not making any errors here. And we developed the following model. I won't go into this. The idea is the following. If you want to calculate the thermal conductivity by the equation, you need to make sure that what you are measuring is amorphous solid. And the dominant phonon wavelength is in Bismuth, and this is the velocity of sound inside the Bismuth, is 0.4 nanometers. Now, based on this equation here, which I won't go into the details how this is extracted, it calculates the mean free path of what is called skip the terminology. This is the mean free path of phonons that are going here with vanishing wave vector, which is perpendicular to the main axis of the wire. And the mean free path here is 1.4 nanometers, which is exactly the phonon wavelength, the dominant phonon wavelength of the Bismuth. What it means is that if you have a mean free path, which is exactly this, it means that you have an amorphous material. And if you have an amorphous material, you can put all the values inside and calculate theoretically what you would expect to see for the thermal conductivity, and it's 0.07. Experimentally, what we measure is 0.08. So that is quite nice. So now we have everything. We have the Seebeck, we have the electrical conductivity, and we have the thermal conductivity. All you have to do is plug them into the equation and see what we get. And this is what we get. We cross the 3.
The device is much longer than 0.1 nanometer.
Yeah.
You said it's ballistic.
It's ballistic. This is the phonons. It's ballistic in terms of the electric carriers. But the phonon is something to do with it. So we cross, here it is, we have the 3, the number. I mean, we have a thermoelectric device operating at 7078 with a ZT value that is crossing 3. This has never been reported before, which I think is quite nice. The question is, how can we make it work at higher temperature? Now, at higher temperatures, you would expect that the thermal conductivity is going to be much higher, which is not good. But then, you need to remember that the Seebeck has units of entropy. It means that if you take the 2 more minutes, I'm done. So if you at low temperature, if this is entropy, the Seebeck is actually going to be smaller than what the Seebeck is going to be at higher temperature. It behaves like entropy. So we'll have to see, but we expect that we might be able to reproduce the same values also at room temperature, and then we have the technology with ZT about 3, and this is what people are looking for. And I think that since I don't have more time, I'll stop here. That's it.
How do you confront this G?
רגע, כועסים עלינו.
Maybe I missed it, but how do you control this G?
Here. So the wire has, once you make the wire, you have one conductor. But then you shrink it. So you have a method by electromigration process that makes this bow-tie shape, and you can change its control. So you can actually follow the process, and as you shrink it, the conductor is going down, and you can reverse the process. So we can stop whatever we like. I mean, tell me the conductor that you want to measure, and I can stop.
You attributed the properties of this wire to this narrow neck that is shown here. But actually, all your measurements were done over the whole wire, the thick end. So how do you extract the special properties?
That's a good question. So what we do is the following. I didn't go into the details here. So you have let's say a 60 nanometer like 50 nanometer in length of a wire, and the constriction is much smaller than that. So you have a delta T over this structure. You can assume that this delta T is linear, so then you know what should be the delta T over your constriction and calculate the C-back based on what you're measuring, because the C-back of the constriction is much higher than everything else that is contributing.
Because that's the dominant feature. Okay.
It looks like excellent work.
Looks like excellent work, but I'm wondering about two potential issues. One of them, what about the p-type? I mean, you need a couple, right? And the other one is these wires, what would they be put on? It seems like anything above vacuum would create a problem for the thermal conductivity. So what kind of substrate can you encapsulate that into?
Well, it's okay. Let's all right. So first of all, this is purely intrinsic, so we didn't dope it. The next thing to do is to dope it. We can dope it either N-type or P-type and reproduce the measurements to see the properties as a function of doping. So this I didn't talk about this at all.
But it had a sign.
What?
The Seebeck effect, Seebeck coefficient had a sign, right? It was
the Seebeck coefficient has a sign, and here, because it was intrinsic, it was because of the electrons are the dominant carrier, because they are the mean free, the effective mass is much smaller, then they are contributing to Seebeck here, and then once we have the gap forming, the holes are the dominating one. Once we dope it, it's going to be completely different. We need to do it in order to understand what is happening. And in terms of what is the surrounding of the wire, you don't care, right? You don't care. What you are characterized here is the efficiency of this material at all. I mean, it doesn't matter what.
I mean, in the future device.
Even in the future device, I mean, whenever you make a thermoelectric material, okay, you take the best thermoelectric material that you can get in order to have that maximum efficiency of reconstruction, regardless of what is surrounding. So for the same surrounding environment, these Bismuth wires will behave the best that you can. That's the important.
We can take it offline.
Perfect. So I think we should thank Yoram again.